People grow up thinking the planets are waiting for us, like the only thing standing between humanity and the stars is better technology and a little more time, but the closer you look, the worse it gets. Space is not just far, it is built to defeat you. Distance is only the first problem. Then speed fails. Fuel punishes you. Radiation starts damaging you. Your body starts changing. Your systems start wearing out. And even the places you dream about reaching often turn out to be hostile anyway. This is not a story about why space travel is hard. It is a story about why the universe may be arranged in a way that makes human access to other planets far less realistic than we ever wanted to believe. The first mistake people make about space is thinking planets are close. You hear the names so often that they start to feel familiar. And familiar things feel reachable. Mars sounds like the next world over. Jupiter sounds far but still part of the same neighbourhood. That is already the wrong way to think about it. In space, even the places we call nearby are separated by distances so large that normal human language starts to fail. Take Mars first, because Mars is the planet people always use when they talk about the future. It is the closest serious target for human travel. It is the one that makes the dream sound practical. But even Mars is not close in any everyday sense. Mars is about 228 million kilometers from the Sun on average, around 141.7 million miles. And the distance from Earth to Mars is not fixed. Both planets keep moving, so the gap changes all the time. At the closest useful alignment, Mars can be about 54.6 million kilometers away, around 33.9 million miles. At the far end, it can be about 400.2 million kilometers away, around 248.7 million miles. That one fact already destroys the casual version of this topic. When people say Mars is next door, they are using Earth language for a problem that does not behave like anything on Earth. On Earth, close means you can get there quickly if you really need to. In space, close can still mean a gap so huge that every system on your spacecraft has to keep working for months in a place that gives you nothing for free. No air, no pressure, no repairs, no rescue. No margin that feels normal. And Mars is the easy example. That is the important part. Mars is the comforting example. Mars is the planet people bring up when they want space travel to sound realistic. So if even Mars is this far away, then the rest of the solar system is not a roadmap. It is a scale problem most people never really measure. Then the picture gets worse. A lot of people think the solar system ends somewhere around Pluto. That is not true. Pluto is not the edge. The Kuiper belt is not the edge either. Far beyond that, there may be the Oort cloud, a huge distant reservoir of icy bodies that may begin around 2,000 to 5,000 astronomical units from the Sun and stretch out to 10,000 to 100,000 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, so now you're not talking about a few planets in a neat arrangement. You're talking about a system so extended that its outer boundary may reach roughly 1/4 to halfway toward the next star. That is the point where most mental pictures of the solar system completely break down. People think of it as a compact collection of worlds. It is not. It is a massive zone of gravitational control with a frontier so far away that even our best machines barely make a meaningful dent in it. And the comparison that really matters is Voyager 1. This is the farthest human-made object ever launched. It has been moving away from the Sun for decades. It is one of the great engineering achievements in human history. And even at its current speed, it would take about 300 years just to enter the Oort cloud, and maybe 30,000 years to get beyond the outer edge. That is not a dramatic exaggeration. That is what the scale of our own solar system does to one of the greatest spacecraft we have ever built. So the solar system is not a tidy group of destinations waiting to be crossed one after another. It is a structure so large that once you use real numbers, the whole tone changes. Mars stops looking close. The outer planets stop looking distant but manageable. And the phrase other planets starts sounding much less like the next step of exploration and much more like a statement people repeat before they actually do the math. Then there is another number that makes this even more direct. Light, the fastest thing in nature, takes about 3 to 22.4 minutes to travel between Earth and Mars, depending on where the planets are in their orbits. That matters because a radio signal moves at the speed of light. No mass, no fuel, no engine, no shielding, no human body. And even that can take several minutes one way just to cross the space between two planets in our own system. That should completely reset your sense of scale. Because people often assume that distance only matters for slow things. It does not. Distance is still there even when you move at the maximum speed the universe allows. So if light itself needs minutes to cross ordinary planetary space, then human vehicles moving vastly slower are not overcoming that gap in any simple sense. They are spending long periods surviving inside it. And this is where the discussion stops being casual. Because once you accept that planetary distances inside our own solar system are already huge, the next step is obvious. The nearest star system does not solve the problem, it makes it much more severe. Proxima Centauri, the nearest star system to ours, is about 40.208 trillion kilometers away. That is roughly 25 trillion miles, or about 4.25 light years. And that number changes everything. Inside the solar system, the main question sounds like engineering. Can we build something strong enough, light enough, reliable enough, and fast enough to make the trip? The moment you move outside the solar system, the question changes. Now the issue is not just machinery, it is time. Because 40 trillion kilometers is not just a very large travel distance, it is a distance that makes normal human travel concepts stop working. It is not a long trip, it is a completely different category of problem. Even the nearest exoplanet does not make the story easier. It shows you how far away the easiest interstellar target really is. So the escalation is clear. First, planets seem close only because people speak about them casually. Then the actual Earth to Mars distance shows that close in space still means a giant void. Then the outer solar system reveals that even our own system is vastly larger than most people think. Then light travel time makes the distance feel more real, because even the fastest possible signal cannot make planetary space feel small. And finally, the nearest star system removes any remaining comfort. Beyond the solar system, the problem is no longer just travel. It becomes whether human beings are even using the right tools, the right timescales, and the right assumptions for a universe built this large. That is the first wall in this whole story. Before you talk about engines, radiation, food, landing, or survival, you have to get past the basic fact that space is not empty in the way people think. It is empty in a much harsher way. It is empty across distances so extreme that the word nearby becomes misleading, then useless, and finally ridiculous. And if the distances are already this bad, then the next question gets even worse. It is not just how far the planets are, it is how slow we still are compared to the scale we are trying to cross. The problem is not just distance. The real problem is distance divided by speed. That is where the whole dream starts to break. People hear a number like 430,000 miles per hour and think that has to be enough for space. On Earth, it sounds absurdly fast. In space, it is still slow. Look at the best machines we have. Voyager 1, the farthest human-made object ever sent out, is moving at about 17.0 kilometers per second. That is roughly 38,027 miles per hour. New Horizons left Earth at about 58,500 kilometers per hour, or about 36,400 miles per hour. Parker Solar Probe, at its fastest point near the Sun, reaches around 687,000 kilometers per hour, or roughly 430,000 miles per hour. Those numbers are real. They're impressive. They represent decades of engineering, planning, and precision. But this is exactly where people get misled. A speed can be impressive and still be nowhere near enough, because speed does not mean much by itself. It only means something when you compare it to the distance you're trying to cross. That is the part people skip. A spacecraft can set records and still lose completely against the scale of space. A number that looks huge on a launch graphic can become almost useless once you stretch the map out to planetary and interstellar size. So when people say we already have incredibly fast spacecraft, that is true in a narrow technical sense. But when you ask whether those speeds are enough to make other planets realistically reachable for humans, the answer changes very quickly. then the question gets harder. If these are our record speeds, what do they actually buy us? This is where the emotional reversal happens. Fastest spacecraft ever sounds like progress. It sounds like momentum. It sounds like the beginning of a road outward. But when you turn that phrase into the travel time, it stops sounding inspiring and starts sounding brutal. At Voyager 1 speed, a trip to Proxima Centauri would take roughly 75,000 years. That is not a hard mission. That is a timescale longer than all of recorded human civilization. If you take New Horizons' launch speed, which was one of the fastest departures from Earth ever achieved, you still get roughly 78,000 years to Proxima. So even our best practical departures barely change the verdict. And then there is Parker Solar Probe, which gives people false hope because the number is so extreme. Around 687,000 kilometers per hour sounds like the kind of speed that should finally make the stars feel closer. It does not. Even if you pretend you could keep that speed going in the right direction forever, which you cannot, the trip to Proxima still comes out to about 6,700 years. That is the optimistic fantasy version, and it's still completely outside any mission model that makes human sense. So the phrase fastest spacecraft ever does not mean what people want it to mean. It is not proof that interstellar travel is getting close. It is proof of how far away the stars really are, even when human engineering performs at its absolute best. The timetable barely moves into a range that still sounds impossible. That is the real lesson of these speed records. We have learned how to launch machines very fast by human standards. We have not learned how to cross interstellar distance on human timescales. Then people usually say, fine, forget the stars, Mars is different. And yes, Mars is different. But only partly. Mars is much closer than Proxima Centauri, and that matters. That is why Mars stays in the conversation at all. But closer does not mean easy. Closer means you move from impossible on civilizational timescales to brutally difficult on mission timescales. If you do a very simple comparison and take Voyager 1 speed, about 17 kilometers per second, and point it at Mars' average sun distance of 228 million kilometers, you get roughly 155 days. That is already months, and that is using a simplified straight-line idea that real spaceflight does not get to use. Real missions do not fly across space like a bullet toward a target. They follow transfer paths shaped by gravity, fuel limits, launch windows, and the fact that both planets keep moving. So even in the inner solar system, speed is not just about going fast. It is about keeping a payload alive, powered, shielded, navigated, and functional long enough for the trip to finish. That changes everything. A fast engine is only the start of the problem. After that, every day in space becomes part of the cost. And that is why this section matters so much. The inner solar system turns into months-long missions, even when the target is the nearest Sirius planet. The outer solar system turns into years or decades. And beyond that, the numbers become so large that speed headlines start sounding almost irrelevant. Space does not care whether a number looked exciting back on Earth. It only cares how long your systems have to survive. Then comes the final trap in this section. People hear about Parker Solar Probe and assume the speed problem is being solved. But Parker's record speed does not mean what people think it means. Its peak velocity happens deep in the sun's gravity well. It is a special situation. It is the result of falling through an extreme gravitational environment and using orbital mechanics in a very specific way. That is not the same as a sustained cruise speed you can aim at another star and keep for thousands of years. It is not even close to that. It is a local speed achievement under special conditions. It proves we can move a small robotic probe very fast near the sun. It does not prove we can send a crewed vehicle with shielding, food, water, redundancy, life support, repair equipment, and long-term reliability out toward interstellar space at anything remotely similar. That is the context people usually miss. A probe making a high-speed pass near the sun is not the same thing as a ship maintaining deep space cruise. One is a record under special conditions, the other would be an entire transportation system. And once you add human survival to the equation, the situation gets even worse. Now the vehicle is heavier, now it needs protection, now it needs supplies, Now it needs systems that keep working for years, maybe decades. Every requirement pushes mass upward, complexity upward, and practicality downward. So this is the wall. Not just distance, but speed. Not just big numbers, but the fact that our best speeds are still tiny compared with the scale we want to cross. Every time a propulsion headline sounds like a breakthrough, you have to ask one question. Fast compared to what? Compared to a jet, yes. Compared to a rifle bullet sometimes. Compared to the gap between stars, not even remotely. And once you accept that, the next problem gets even worse. Because if going faster is already this hard, then what happens when you try to get that speed using rockets, and every gain in speed starts punishing you with more fuel, more mass, and less margin? The next problem is worse because it sounds like something engineering should be able to fix. If the issue is speed, why not just build a bigger rocket? That feels like the obvious answer. It is also where spaceflight turns brutally unfair. Rockets do not reward you in a straight line. They punish you for wanting more. The basic rule is simple, even if the math behind it is not. To get more speed, you need to throw propellant out the back. But to throw more propellant, you have to carry more propellant. And the moment you carry more propellant, your vehicle gets heavier. Then you need even more propellant to move that extra propellant. That is the trap. The rocket equation is not a detail engineers worry about after the exciting part. It is the law that decides how bad the trade gets every time you ask for more speed. This is why spaceflight always ends up looking extreme. Giant tanks, tiny payload fractions, staging, ruthless mass cuts, endless arguments over kilograms. It is not because rocket designers are being overly cautious. It's because once you are using a rocket, mass becomes a kind of enemy that grows faster than your intuition expects. Every extra thing you want to carry makes the whole vehicle harder to move. More structure, more shielding, more food, more spare parts, more habitat volume, more redundancy, more safety margin, all of it comes back to the same problem. The rocket has to push it all. And the harder you want to push it, the more the vehicle gets swallowed by its own propellant demand. That is why rockets look so disproportionate. The part people care about, the crew, the probe, the science package, the actual mission, is often a tiny fraction of the full launch mass. Most of the machine is there because the machine has to spend most of itself just to get the mission moving. So when people casually talk about going faster, they're usually talking as if speed is just an upgrade. In Rocketry, speed is expensive in the most punishing possible way. It does not just cost more fuel, it changes the whole vehicle. Then people usually say chemical rockets have already solved this well enough. And chemical rockets are incredible. They are powerful, they produce high thrust, they are the reason we can leave the ground at all. If you want to get off a planet, chemical propulsion is still one of the most practical tools we have. That part is real, but power is not the same thing as efficiency, and that is where the limit appears. A good liquid hydrogen and liquid oxygen engine can have a specific impulse around 350 seconds in an orbital example. In plain language, specific impulse is a measure of how efficiently the engine turns propellant into useful push. Higher specific impulse means you get more momentum out of the propellant you burn, and chemical rockets, even very good ones, are limited here. They give you strong push for launch and major maneuvers, but they do not give you the kind of long-range efficiency that makes huge distances stop mattering. So chemical rockets are excellent at the first part of the mission and weak at the part people actually dream about. They buy you launch. They buy you escape from a gravity well. They buy you the early minutes when thrust matters most. But they do not buy you a civilization that casually crosses the solar system, and they definitely do not buy you anything like practical interstellar travel. That is the mismatch people keep running into. A chemical rocket can look unbelievably powerful on the pad and still be completely inadequate for making astronomical distance feel small. That is why a mission can succeed at launch and still fail at the larger goal. Leaving Earth is hard, but leaving Earth is not the same thing as making distant worlds easy to reach. The rocket can do its violent job at the start and still leave you with months, years, or much worse afterward. So chemical propulsion is not weak. It is just local. It is powerful in the immediate sense and limited in the long-range sense, and that difference matters more than most people realize. So then the obvious response is to move beyond chemical propulsion, and we have. Electric propulsion is real, and it is one of the best examples of how space engineering keeps finding solutions that also create new problems. Ion engines can be extremely efficient. NASA reported that Dawn's ion propulsion system delivered more than 11 kilometers per second of total change in velocity to the spacecraft. That is a huge achievement for deep space maneuvering. It shows that we do know how to build engines that use propellant much more efficiently than chemical rockets. But the price is low thrust. Very low thrust. Ion engines do not shove a spacecraft hard. They nudge it continuously over long periods. That works very well for robotic missions. A robotic spacecraft can afford patience. It does not need a fast transfer because it is not keeping a crew alive. It does not need heavy radiation shielding for people. It does not need a large pressurized habitat. It does not need life support margins, medical capability, or a schedule built around human health. A robotic probe can let an ion engine push gently for months or years because the mission is designed around that reality. A crewed mission is different. Now mass goes up, now time matters more, now exposure to radiation matters more, now life support and supplies matter more. Now you care about how quickly you can transfer, not just whether you can keep nudging the trajectory in the right direction. So electric propulsion helps, but it does not rescue the main idea. It solves one part of the problem by making another part harder. Highest efficiency is great, but low thrust becomes a serious limitation once you are trying to move large human-rated systems on demanding timelines. And that is one of the deeper patterns in this whole topic. It is not that we have no better engines, it is that every better engine comes with a trade that stops it from being the clean answer people want. High thrust burns through propellant. High efficiency often means low thrust and long mission times. Crewed deep space suffers under both compromises. So the story is not that propulsion research is failing. The story is that the problem itself is stacked against simple wins. Then people go one step further and say nuclear thermal propulsion changes everything. It absolutely matters. But again, the scale of the problem stays in control. Nuclear thermal propulsion has been attractive for a long time because in principle it could reach a specific impulse of roughly 850 to 1000 seconds. That is about double the rough range of chemical propulsion, and that is not trivial. Doubling performance in a field this difficult is serious. It could reduce propellant mass. It could improve some mission architectures. It could make Mars transfers shorter and more flexible. That is exactly why programs like Draco exist. Agencies want to prove that an operable nuclear thermal system can work in space. So yes, this is real progress. It is not science fiction. It is the kind of propulsion improvement that could matter for serious solar system missions. But this is also where perspective matters. Doubling performance is not the same thing as defeating astronomical distance. Better margins are not the same thing as changing the scale of the map. A technology that might improve Mars missions does not suddenly make the outer planets easy. And it definitely does not make another star system feel close. That is the structural point. Even serious propulsion upgrades mostly change the margins. They can shorten trips, they can reduce required mass. They can give planners more options. All of that matters, but they do not erase the fact that planets are very far apart and stars are separated by distances that crush every current mission model. A stronger engine helps. It does not rewrite the size of the universe. So rockets punish you in two ways at once. First, the basic physics of rocketry makes speed expensive in mass. Then every propulsion upgrade that tries to fix that gives you a different compromise. More thrust, worse efficiency. More efficiency, less thrust. Better performance, still not enough to make the stars remotely human scale. That is why the dream keeps hitting the same wall. It is not blocked by one missing breakthrough. It is blocked by a chain of constraints that all connect back to each other. And once you see that, the next problem gets even sharper. Because there is one planet that keeps pulling people back in. One world that looks just close enough, just possible enough to make all of this feel like it might still work. Mars is the planet that keeps fooling people. It is close enough to stay in the conversation and far enough to break almost every system we depend on. That is why Mars matters so much. It is not because Mars is easy. It is because Mars is the nearest serious destination that still exposes how hard planetary travel really is. Mars looks reachable for a reason. You can see it from Earth. It has seasons. It has ice, dust storms, valleys, and polar caps. It is a real world, not just a distant point of light. So people naturally treat it like the first step. They think if we can get to Mars, then the rest is just scaling up. That is the trap. Mars is not the first easy step. Mars is the first place where the full cost of leaving Earth becomes impossible to ignore. And the first problem starts before launch. Earth and Mars do not line up in a convenient way whenever we want. The most energy-efficient launch windows come only about once every 26 months. That means Mars already controls your calendar before the mission even begins. If you miss the window, you do not just leave later that month. You may have to wait more than 2 years for the next good chance. That changes the whole meaning of the trip. On Earth, if conditions are bad, you reschedule. In deep space, the planets decide when you go. The timing is not flexible in the normal sense. It is built into orbital mechanics, so even the nearest serious human destination is not a place you can simply choose to visit whenever you are ready. You have to leave when the solar system allows it. And that should already change how you think about Mars, because a destination that controls your launch date this tightly is not just far away, it is operationally hostile. You are not planning a trip in the normal sense. You are building an entire mission architecture around a moving target and a rare alignment. That means every delay, every missed test, every technical failure, every weather issue, every budget slip can push you into a wait measured in years instead of days. Then the next question gets worse. If Mars already dictates when you can go, what does it demand once you are actually committed? A Mars mission is not a visit. It is an exile. That is the more honest way to say it. Mars is on average about 140 million miles from Earth, roughly 225 million kilometers. But the bigger point is not the average distance by itself. The bigger point is what that distance forces the mission to become. Deep space planning for Mars-class missions often works with a duration of about 1,100 days for at least 4 crew. That is about 3 years. So when people casually say trip to Mars, they make it sound like one long transit followed by an arrival. That is not what it is. It is launch, cruise, surface operations, waiting for return windows, maintaining health, storing supplies, recycling air and water, managing equipment wear, handling isolation, and surviving with limited support for roughly 1,000 days. Mars is not a single event. It is a multi-year system. That is why Mars matters so much in this whole argument. If the nearest serious human destination already forces you into a mission measured in years, then every planet beyond Mars becomes much more than a destination. It becomes a test of whether human biology, mission design, and social stability can hold together long enough to make the attempt mean anything. Once the baseline is 3 years for Mars, the rest of the solar system stops looking like a list of future stops and starts looking like a list of systems we are not yet prepared to survive. And that leads to the next hard question. If a Mars mission lasts that long, how much help can Earth really provide once something goes wrong? This is where the psychological comfort of normal spaceflight disappears. In low Earth orbit, people are used to the idea that help is close. Mission control can respond quickly, cargo can be launched, abort options exist, communication is nearly immediate. Mars removes that entire safety model. A Mars mission may face up to 44 minutes of round-trip communication delay. One-way delay can vary up to about 22 minutes. And depending on planetary geometry and solar activity, communication disruptions can last for days or even months. That means mission control stops functioning like real-time support. Earth cannot talk a crew through a crisis at the speed the crisis unfolds. If something breaks, if someone gets sick, if a landing issue appears, if a navigation error develops, if a serious crew conflict begins, the people on Mars have to deal with it there and then. Earth can analyze later. Earth can advise later. Earth can support in a delayed way, but Earth cannot take control in the moment that matters most. That is a much bigger change than it sounds like at first. Mars is not just far away in kilometers or miles, it is far away in decision-making. That means the crew has to carry far more operational autonomy than people usually picture. They are not just passengers with experts back home, they have to be the experts in the moment of failure. The farther from Earth you go, the more that becomes true. And once that becomes true, another assumption falls apart with it. What happens if the plan fails badly enough that you need rescue? For most of human spaceflight history, rescue has remained part of the mental model, even when the risks were high. In low Earth orbit, you think in terms of aborts, nearby stations, return vehicles, resupply missions, and short timelines. Mars destroys that habit. Orion, for example, can support 4 astronauts for about 21 days without docking. Mars-class planning talks about 1,100 days. Those numbers do not belong to the same category of mission. That difference is not just a matter of scale, it is a different kind of existence. A Mars crew is not riding in a vehicle that can count on quick intervention. They are carrying the systems that must keep them alive for years. That means life support, maintenance capability, medical capability, spare parts, contingency stores, operational autonomy and psychological endurance all have to move from helpful extras to core survival requirements. And that is why Mars is so important in this whole story. It is the closest place where the rescue model mostly dies. Once you get that far, you're no longer assuming that Earth can save you in any normal time frame. You're assuming the crew and the mission hardware must absorb failure locally. That is a profound shift. It means human travel to Mars is not just a harder version of Apollo or the ISS, it's a different category of mission architecture with a much weaker safety net. So Mars keeps doing 2 things at once, and it stays close enough to sound possible, and it stays hard enough to expose what the rest of planetary travel would really demand. That is why it is so dangerous as a symbol. People treat Mars as proof that interplanetary civilization is beginning. In reality, Mars may be the place that proves how fragile that idea still is. Because once rescue becomes weak, everything else has to become stronger. The crew has to be more autonomous, the machines have to be more reliable, the habitat has to be more closed loop, the planning has to be tighter, the medical capability has to be local, the mission has to survive without quick outside correction. And if all of that is already true at Mars, then the phrase other planets stops sounding ambitious and starts sounding structurally premature. That is the real reason Mars matters. It is not the easy planet, it is the least impossible serious one. And even that world forces you into rare launch windows, multi-year timelines, delayed support, weak rescue, and near total operational independence. So if Mars already pushes the human mission model this far, then the next question gets even more uncomfortable. Because even if you accept the distance, the delay, and the lack of rescue, there is still the environment itself, and that environment is not neutral. It starts damaging you the moment you leave Earth's protection. The next problem is not distance or speed. It is the fact that space itself starts working against your body the moment you leave Earth's protection. A lot of people think the main danger is vacuum. Vacuum is real, but is almost the simple part. The deeper problem is radiation. Earth protects you from more of it than you notice every second of your life. You live under 2 layers of protection. One is the atmosphere above you. The other is Earth's magnetic field, the magnetosphere, which helps deflect and reduce some of the charged particles coming from the sun and from deep space. Most people never think about that because it is always there. It is built into normal life. You do not wake up and think about being shielded from galactic cosmic rays or solar particle events. But the moment you leave low Earth orbit, that protection starts dropping away, and the environment changes fast. That is why radiation is not a side problem in deep space, it is one of the core hazards. Once you go beyond the region where Earth is protecting you, you are not entering some clean, empty zone. You're entering a place where high-energy particles keep moving through your vehicle, your electronics, and potentially your body. Biology did not evolve for that. Human beings evolved under a thick atmosphere and inside a magnetic field. deep space removes both advantages at the same time. And that matters because multi-year missions are not short exposures. The damage is not just about one bad moment, it is about continuous exposure over long periods. That changes the whole picture of interplanetary travel. Now your ship does not just need propulsion, air, water and power, it needs to reduce an invisible environmental threat that does not stop just because your mission is going well. Then the next question becomes very direct. Is this just a theoretical concern, or do we already know what the Mars route does? We already know. This is one of the most important parts of the whole topic, because the numbers are measured, not guessed. Curiosity carried a radiation assessment detector during its cruise to Mars. It measured about 1.84 millisieverts per day during transit. That gives the discussion a very different tone, because now the route is no longer something people are estimating in the abstract. We have already sent a detector through it and measured the environment along the way. For Curiosity's 253-day trip, that works out to about 466 millisieverts for the transit. And if you think in terms of a return architecture, NASA technical discussions use a number around 662 millisieverts before you even fully count surface exposure. That is the part people need to understand clearly. The problem is not fictional. It is not speculative. It is not a dramatic extra thrown into the story to make Mars sound more dangerous than it is. The route itself has already been measured, and the route is harsh. Every extra day in cruise adds more than delay. It adds dose. So when people talk about faster transfers, they are not just talking about convenience. They are talking about reducing how long the crew has to stay inside a radiation field that keeps working on them the whole time. That means radiation is tied directly to speed, mission, duration, and propulsion. The longer you take, the more exposure builds up. The heavier your shielding, the harder the vehicle becomes to launch. There is no clean separation between these problems. And once you see that link, the obvious response sounds simple. Add shielding, make the walls thicker, protect the crew better. But the moment you say that, the rocket problem comes back. Shielding is heavy, and heavy is the enemy in spaceflight. If you want more protection, you usually need more mass. More mass means more propellant. More propellant means a larger launch burden, a larger vehicle, more structural demand, more cost, and usually more mission complexity. That is why radiation is such a difficult engineering problem. The most obvious safety fix directly worsens some of the other hardest parts of the mission. Hydrogen-rich materials such as water and polyethylene are often discussed as useful for radiation protection. That makes sense, and it is one of the smarter ideas in deep space design, because some of the things you already need can also help shield the crew. Water is a consumable, but it can also function as partial armor. In theory, that is elegant. In practice, it is punishing. Every kilogram of water that helps protect the crew is still a kilogram. The launch system has to accelerate. Every extra layer that improves safety also increases mass pressure somewhere else in the mission. So radiation is not a separate box on the checklist. It spreads through the entire architecture. It changes how much mass you want to launch, how fast you want to travel, how much consumable margin you carry, how you design crew quarters, how you arrange supplies, and how much exposure you're willing to accept during transit. The ship that keeps you alive becomes harder to move precisely because it is trying to keep you alive. Then the topic gets even more severe once you stop talking only about Mars. Mars is the mild case compared with some other parts of the solar system. That is a critical point, because people often assume that if Mars is difficult, the outer planets are just a more distant version of the same challenge. They are not. In some regions, the environment becomes far more extreme. Jupiter is the clearest example. Its particle radiation field is enormous. NASA material for Europa Clipper describes Jupiter's radiation environment as about 20,000 times larger than Earth's Van Allen belts, and about 1,000 times more intense than Saturn's. That should completely change how people hear the phrase outer planets. The problem is not only that they are farther away. In Jupiter's neighbourhood, the environment is much more aggressive. And the evidence for that is built into robotic mission design. Juno needed a titanium radiation vault with walls about 1 centimetre thick. The vault itself weighed about 200 kilograms, roughly 500 pounds, and that was just to protect core electronics. Not a human crew, not a large habitat, not life support, just critical robotic systems that would otherwise be damaged by the environment around Jupiter. That is the real answer to the casual question, why not go to the outer planets? Because distance is only one part of it. Some destinations are not just farther, they are much more punishing once you get there. A place can be physically reachable by trajectory and still be completely unreasonable for human survival. The outer solar system is not one uniform zone of difficulty. In some parts of it, the radiation environment becomes so extreme that even protecting machines is a serious challenge. And that changes the whole emotional structure of the story again. You start with distance, then speed makes distance worse, then rockets make speed expensive, then Mars shows that even the nearest serious destination is already a multi-year systems problem. And now radiation reveals something even more important. Space is not just empty and inconvenient. In the wrong conditions, it is actively damaging. That is why this is such a hard wall for human expansion. The same long trip that strains your food, water, and psychology also keeps exposing you to radiation. The same shielding that protects you makes launch harder. The same destinations that sound exciting on a map may have environmental conditions that punish both biology and electronics. So the farther you go, the more the mission stops being about travel in the ordinary sense and starts becoming a fight to keep living systems intact inside a hostile field. And even if you solve part of that with shielding and mission design, there is another problem waiting right behind it. Because the ship is not the only fragile system out there. The crew is fragile too, and the human body starts changing in deep space much faster than most people realize. The next problem is even more uncomfortable, because it is not mainly about the ship, it is about the people inside it. Human bodies are built for Earth. That sounds obvious, but in space it becomes a serious engineering limit. The body is not a flexible all-purpose system that can work anywhere with a little training. It is adapted to one planet, one gravity level, one atmosphere, one magnetic shield, and one set of daily physical conditions. Once you leave that environment, the body does not just feel uncomfortable, it starts changing. One of the clearest examples is bone loss. During long missions, astronauts can lose around 1% to 1.5% of bone density per month, with the hip and spine especially affected. Other NASA material says losses can reach around 1% to 2% per month without effective countermeasures. That is a serious rate. On Earth, bone loss usually happens gradually over years. In space, it can begin on a timescale of months. That means a deep space crew is not just traveling through space while staying physically the same. The mission is moving outward while the body is being pushed away from the conditions it knows how to maintain. That should change the tone of the whole discussion. A Mars mission is not just about getting a crew there alive, it is about getting them there in condition to work, think clearly, move safely, land, operate equipment, handle emergencies, and eventually return. If the body is steadily losing bone and muscle during transit, then the mission is not simply carrying explorers, it is carrying a biological system that is being degraded by the trip itself. And it is not just bone, muscle loss comes with it. In microgravity, the body does not have to support its own weight the way it does on Earth. Muscles that are normally used every day become less necessary. So unless the crew works actively against that process, their bodies adapt in the wrong direction for the mission. This is one of the least intuitive parts of space travel. The human body is efficient, but it is efficient in a way that hurts you here. If gravity stops demanding constant effort, the body starts giving up the systems it thinks it no longer needs. So the obvious response is exercise. And yes, exercise helps, but this is where the reality becomes much harsher than the usual version people imagine. Exercise in deep space is not a nice habit or a good wellness routine. It is a medical requirement. Deep space planning says future crews may need to exercise for several hours every day to help maintain bone and muscle mass. Several hours every day. That single fact tells you how unnatural long-duration spaceflight really is. The environment is so wrong for the human body that a major part of the daily schedule has to be dedicated to resisting it, and that has consequences everywhere else in the mission. Exercise equipment takes mass, it takes volume, it takes power, it takes maintenance, it adds vibration issues, hardware issues, spare part issues, scheduling issues, and crew time demands, and the time itself matters. On a Mars-class mission, every hour is already under pressure. There are system checks, maintenance tasks, navigation tasks, scientific work, hygiene, food preparation, communication, health monitoring, and rest. Then on top of all that, the crew has to spend hours fighting the environment just to avoid getting weaker. That is what deep space travel actually looks like once you strip away the simplified version. You're not just launching a vehicle, you're launching a moving life support system, a repair shop, a medical station, and a forced daily countermeasure program, because the passengers are built for Earth and Earth only. The mission has to spend resources not just on moving forward, but on stopping the crew from physically degrading while they move. Then the problem gets more disturbing because it is not limited to bones and muscles. Microgravity also affects the body in ways that are harder to predict and harder to explain simply. One of the biggest concerns is spaceflight-associated neuroocular syndrome, or SANS. NASA treats this as a major health risk connected to long-duration spaceflight. In basic terms, microgravity shifts fluids toward the head. On Earth, gravity helps distribute fluids differently through the body. In space, that balance changes, and when it changes, it can affect the eyes, vision, and pressure conditions inside the body in ways that are still being studied. That matters because it breaks another easy assumption people make. A lot of people picture long missions as physically tiring, but basically manageable, like a crew arriving worn out and then recovering. The real concern is more serious than that. The crew may arrive changed by the trip in ways that are not just about fatigue. Vision changes are not a minor detail on a mission that depends on reading systems, monitoring data, performing procedures, piloting vehicles, operating tools, and making good decisions in dangerous environments. If the journey itself can alter visual function and internal body dynamics, then the problem is not just endurance. It is whether the crew arrives with the same capabilities the mission depends on. And this is where the story stops being just a list of hazards and becomes something deeper. It means we are not only struggling to build the right spacecraft, we are also still trying to understand how the species inside the spacecraft behaves when removed from Earth for long periods. Space does not simply challenge human strength, it challenges human physiology at a systems level. Then the final problem in this section makes everything even less certain. Even if we accept that microgravity is bad for the body, there is still one hope people fall back on. Maybe Mars gravity is enough. Maybe once the crew gets there, the body stabilizes. Maybe partial gravity solves enough of the problem to make long stays realistic. But the truth is that we do not know that yet. Mars has about 0.38 of Earth's gravity. That is more than microgravity, but much less than what the human body evolved under. And right now, we do not have enough evidence to say with confidence that this level is enough to protect long-term human health. NASA's hazard framework treats gravity and lack of gravity as a major risk, partly because the data are still incomplete. That means Mars is not just a hard destination. It is also an unfinished biological question. Maybe partial gravity helps enough to reduce bone and muscle loss to manageable levels. Maybe it helps some body systems but not others. Maybe recovery is possible after return. Maybe some changes remain serious. We do not know enough yet, and that uncertainty is not a side note, it is central. A civilization cannot responsibly build long-term settlement plans on a biological maybe. That is one of the hardest truths in this whole topic. We are not blocked only by engines, fuel, radiation, or distance. We are also blocked by incomplete knowledge about whether human bodies can remain healthy, capable, and functional in the environments we want to reach. It is not enough to land on Mars if the body cannot reliably tolerate the trip there, the stay there, and the trip back in a way that scales beyond a few exceptional crews. So by this point, the pressure is coming from every direction at once. Distance makes missions long. Long missions increase radiation exposure, shielding adds mass, mass makes propulsion harder, and the same long duration that breaks the vehicle design also starts breaking the crew. That is why the idea of casually reaching other planets keeps collapsing when you look at it closely. It is not one problem, it is a stack of interacting limits, and the human body is one of the weakest points in the stack. And even if you somehow keep the crew alive and functioning, there is still another problem waiting inside the ship itself. Because a crew cannot survive on stored supplies forever. The ship has to keep recycling and recovering and reusing the basics of life over and over again, with almost no failure allowed. A lot of people assume life support is already basically solved. That is one of the biggest misunderstandings in all of space travel. They picture a spacecraft as a sealed machine that just keeps people alive if you build it well enough. But long-duration life support is not a box you check once and move past. It is a constant chemical, mechanical and biological struggle, and the numbers make that very clear. On the ISS, NASA recently reached a 98% water recovery goal. That is a major achievement. Deep space planning also says long missions need at least 98% water recycling and about 75% oxygen recovery from exhaled carbon dioxide. Those numbers sound impressive, and they are, but they also reveal the problem. The reason engineers care so much about getting that high is because anything lower starts costing you mass immediately. If you are not recovering enough water, you need replacement water. If you're not recovering enough oxygen, you need replacement oxygen, or the hardware and chemistry to make up the gap. Then you need filters, spare parts, backup hardware, contingency reserves and maintenance tools to keep the whole system running. So the real message in those percentages is not that life support is finished. It is that life support is still one of the main things threatening the mission. The closer you are to Earth, the easier it is to hide that fact. In low Earth orbit, if something is not perfectly closed, you can still lean on resupply. That makes the system look more complete than it really is. But the moment you start talking about Mars or anything beyond Mars, that illusion breaks. A long mission cannot survive on the assumption that fresh cargo will keep arriving to patch every loss. And that means the next question gets much more serious. If we are recycling this much already, what is still being lost? The weak point is that even the current state of the art is still only partially closed. NASA's next-generation life support work points out that the ISS Sabatier system produces methane, and because hydrogen is not fully recovered, about half of the carbon dioxide stream is effectively lost in a way that costs oxygen recovery. That is a very important detail because it shows the difference between a system that works and a system that is truly self-sustaining. Those are not the same thing. A partially closed loop can be good enough near Earth. It can support missions very successfully, but it is still leaking value. It is still throwing chemistry away. And once the mission gets far enough from Earth, every leak stops being a routine engineering imperfection and starts becoming mission risk. Distance changes the meaning of inefficiency. A system that is acceptable in low Earth orbit can become dangerous in deep space because there is no practical way to keep feeding it makeup supplies whenever it falls short. That is why this section matters so much. People often hear about recycling systems and assume the bigger problem has been solved. The more honest version is that the systems are improving, but they are still not closed enough for the kind of planetary scale independence people usually imagine. The farther you go, the more punishing that gap becomes. A life support loop that is not fully closed is not just inefficient, it is a steady drain on mission margin. Then the issue becomes even more concrete when you stop talking in percentages and start talking about one crew member at a time. NASA notes that each astronaut needs about a gallon of water per day for drinking, food preparation, and hygiene. That does not sound huge at first. A gallon feels manageable. But space punishes small numbers when you multiply them by time, people, and failure margin. Now take that gallon and multiply it by multiple crew members, then by years instead of days, then add contingency stores, then add the reality that the recovery hardware itself has mass, power demands, maintenance needs, and failure points. Suddenly water is not just something the crew drinks. It becomes one of the central substances in the mission. It is part consumable, part shielding, part hygiene system, part medical necessity, part thermal and chemical planning problem, and part vulnerability. If the water loop performs badly, the mission suffers everywhere, and that is why deep space habitats are much harder than capsules. A capsule can survive a trip. A capsule can be relatively simple because the mission is short enough and close enough that you are not asking the vehicle to behave like a permanent ecosystem. A deep space habitat is completely different. It has to keep cycling water, air, waste, humidity, contaminants, and hardware performance over and over again for months or years. It does not get to have a bad week. It does not get to wait for a maintenance shutdown. It does not get to call for a replacement truck. It has to keep operating like a small industrial ecosystem with human lives inside it the entire time. And once you see it that way, the whole idea of a ship to another planet changes. It stops looking like transportation and starts looking like a very fragile biosphere. That is the real picture NASA's habitation work points toward. Atmosphere, water, microbes, floating particles, fire risk, health maintenance, radiation protection, food storage, suits, waste processing, all of these are connected. They are not separate boxes on a mission checklist. They are parts of one closed environment that has to stay stable while moving through a place that offers it no help at all. That is why interplanetary travel is so much harder than people think. The ship is not just a vehicle, it is a stitched-together living system. It has to carry a functioning slice of Earth with it. Not all of Earth, obviously, but enough of the important parts to keep people breathing, drinking, eating, cleaning, repairing and staying alive without the ordinary background support that life on Earth gets for free. And even on Earth, building stable closed environments is hard. It is hard with gravity. It is hard with full industrial supply chains. It is hard with weather, open space, rapid resupply and room to improvise. In deep space, you lose all of those advantages. There is no buffer outside the hull. There is no forgiving environment. There is no easy way to vent a problem and replace what you lost. If the ecological balance inside the vehicle starts slipping, the crew is trapped inside the slipping system. That is the deeper reason this keeps collapsing under realistic analysis. Reaching another planet is not mainly about propulsion. Propulsion gets all the attention because launches are dramatic and engines look powerful. But once the trip becomes long enough, the core challenge is whether you can carry a self-maintaining human environment with you and keep it stable despite hardware wear, limited mass, limited power, psychological strain and no meaningful resupply. So by this point the picture is very different from the popular version. Distance is already a problem. Speed is still too low. Rockets punish mass. Radiation pressures the vehicle design. Human bodies degrade in transit. And now life support adds another layer of difficulty, because even the most advanced systems we have are still not closed enough to make deep space independence feel routine. The mission is not just moving a crew from one place to another. It is trying to preserve an artificial ecosystem for years, with almost no margin for failure. And that leads to another problem people underestimate until they think through the timeline. Even if the ship is working, even if the crew is alive, and even if the life support loop is holding together, distance still damages something else. It damages command, rescue, and human judgment itself. Distance does not just make space travel longer, it makes it less controllable. That is a big shift, because most people still picture human spaceflight using the same basic model we have used for decades. The crew does the hands-on work, and experts on Earth watch everything, guide everything, and step in when something goes wrong. That model starts breaking the farther you go. At Mars distances, communication delay can reach up to 44 minutes round trip. One message goes out and the answer comes back so late that the critical moment may already be over. That means mission control stops working like live support. It cannot coach a crew through a fast emergency. It cannot react at the speed of a failure cascade. It cannot watch a bad situation form and then cut in before the crew makes the wrong call. By the time Earth responds, the decisive part is often already finished. That changes the mission much more than people realise. It means the crew cannot just be operators waiting for advice from a large support team back home. Each person has to carry far more skill, judgment and independence. They have to act like pilot, engineer, medic, systems analyst, and sometimes psychologist, all while the situation is still unfolding. And that matters because hesitation can be fatal. A pressure problem, a fire, a toxic leak, a medical emergency, a landing anomaly. None of these wait for Earth to finish thinking. So distance is not just stretching the mission in time, it is changing who is actually in charge in the moment that matters most. The farther you go, the less real-time authority Earth has. That means distance is not only a transportation problem, it is a governance problem. It changes how decisions are made, where expertise has to sit, and how much of the mission's survival depends on the people physically trapped inside it. And then the next part makes it worse. What does delay do to people, not just procedures? Communication lag is not just an operational inconvenience. It affects behavior. NASA's reviews link delayed communication with increased stress, frustration, adverse behavioral symptoms, and reduced individual performance. That matters because people often picture delay as just silence between messages. In reality, delay changes the emotional structure of the mission. It makes people feel more alone, less supported, and less certain that the people on Earth fully understand what they are dealing with. That gap matters in both directions. The crew cannot rely on Earth in the way astronauts in low Earth orbit can, but Earth also cannot fully rely on its picture of the crew's situation. By the time a report is received, analysed and answered, conditions may already have changed. So the farther out you go, the more every decision lives inside uncertainty. The crew knows Earth is there, but not in the immediate way that matters during stress. Earth knows the crew is out there, but not with enough immediacy to fully share the burden of fast decisions. That is why autonomy is not just a technical feature, it is a psychological load. It sounds good in mission planning documents because it implies competence and resilience, but autonomy under stress means something harsher. It means solving high-stakes problems while isolated, tired, exposed, and fully aware that nobody can take over for you in real time. It means the mission depends not just on engines and hardware, but on whether human beings can stay sharp, cooperative, and emotionally stable, while carrying more responsibility than any crew in past human spaceflight has ever had to carry. Then there is another hard question. If this is already true for humans, how hard is it even for robots? It is already difficult enough that Mars robots do not work alone. Rovers on Mars do not have line of sight to Earth all the time. For about 12 hours per day, they can be in positions where direct communication is not available. On top of that, the light time delay between Earth and Mars can range from about 3 to 22.4 minutes one way. So even on the nearest practical planet, communication is not a simple straight line between robot and home. That is why Mars missions rely on infrastructure. Rovers often send data to orbiters around Mars, and those orbiters relay the information back through the deep space network. The relay system can support data rates up to about 2 megabits per second, which is far more practical than expecting every surface machine to blast directly to Earth all the time, with huge antennas and large power demands. In other words, even robots on Mars need a communications ecosystem spread across multiple spacecraft and across 2 worlds. That is a very important point because it changes what a human Mars mission actually is. It is not just a ship problem, it's not just a lander problem, it is an infrastructure problem. To keep a mission functioning, you do not only need the crew vehicle and the surface systems, you need orbiters, ground stations, relay planning, timing networks, bandwidth management, and a larger communications architecture that stays healthy for the whole mission. Without that support web, even robotic operations become much harder. And human missions are far less tolerant of communication failure than robots are. So when people say why not just send people to Mars, they are usually imagining one main vehicle making the trip. The real answer is much larger than that. You need a network, you need a planetary support structure, you need the kind of layered communications and mission backbone that makes the whole operation even possible. That means interplanetary travel is not just about crossing the distance once, it is about building and maintaining enough off-world infrastructure to make the distance manageable at all. And then the final implication becomes unavoidable. What happens when the problem is not navigation or data, but a human emergency? At that point, medicine becomes local whether you like it or not. If a crew member gets seriously sick, if there is a suit breach, if there is decompression, if something toxic leaks into the habitat, if a critical system starts failing, the crew cannot pause and wait for Earth to reason through the situation. The delay is too long, the rescue is too far away, the decision has to happen where the danger is happening. That forces a major shift in what deep space crews have to be. In the old model, the crew is backed by specialists on Earth. In the Mars model, the crew increasingly has to contain those specialists within itself. That means medical expertise, engineering expertise, operations expertise, systems troubleshooting, and crisis leadership all have to move on board. The crew does not just perform the mission, it carries a missing layer of civilization with it. That is the burden people usually skip over. Reaching other planets is not only a propulsion challenge, it is a human expertise challenge. You need crews who can diagnose problems, treat injuries, manage conflict, repair systems, make hard calls under uncertainty, and keep functioning without immediate support from the planet that built them. And they have to do that while also being the people exposed to the danger. They are the operators, but they are also the patients. They are the decision makers, but they are also the ones whose lives depend on those decisions. So distance keeps doing more damage the longer you look at it. First, it makes the trip longer, then it weakens rescue, then it breaks real-time command, then it increases stress and uncertainty. Then it turns communication into infrastructure. Then it makes medicine local and autonomy mandatory. By this point, the mission is no longer just a story about getting somewhere far away. It is a story about whether human beings can carry enough skill, enough stability, and enough support capacity inside a tiny, isolated system to replace the immediate presence of Earth. And even if they can do that, there is still another hard truth waiting. Launch is only the beginning. The real enemy after launch is time itself, because every extra month and every extra year gives hardware more chances to fail. Launch is the part people remember because it is loud, visible, and easy to understand. Reliability is harder to see, but it is much more dangerous. A rocket only has to survive liftoff or once. A deep space mission has to survive every hour after that. And once a mission lasts years instead of days, that becomes the real fight. Voyager 1 is a good example of what deep space reliability actually means. Its signals still reach Earth at about 160 bits per second from a transmitter using around 23 watts, roughly the power of a refrigerator light bulb after travelling through interstellar space. That is an extraordinary achievement. But the important part is not just that the signal is still arriving. The important part is what had to keep working for that to remain true. Electronics had to keep functioning. Thermal control had to keep the hardware within limits. Power systems had to keep producing usable energy. Fault management had to keep the spacecraft from losing itself after years and years of exposure to a hostile environment. That is what deep space success really looks like. Not one dramatic event, but long-term resistance to decay. And once you start talking about human missions to other planets, that becomes much harder than people usually admit. A crewed spacecraft is not just a probe with seats added. It is a much more complex machine with more systems, more dependencies, more failure points, and much less tolerance for downtime. A robotic probe can lose instruments and still continue. A human mission can lose the wrong subsystem and end the mission immediately. That is why reliability stops being a supporting issue and becomes the central issue. Once the mission lasts years, your ship is not mainly proving that it can move. It is proving that it can avoid breaking down for a very long time in a place where breakdown is not acceptable. The mission is not winning a sprint. It is trying not to decay faster than the timeline. Then the next question gets much more practical. What exactly is wearing out? The answer is almost everything. Spacecraft do not fail only because of one dramatic accident. They also fail because normal hardware ages, and deep space is a bad place for aging hardware. NASA's thermal control guidance makes the basic problem clear. A spacecraft has to deal with absorbed heat, stored heat, generated heat, and dissipated heat and every component has to stay inside survival and operating limits. That is already difficult in Earth orbit. It gets harsher in deep space where sunlight changes with distance, shadows can last a long time, and repair opportunities become limited or non-existent. So the damage is not always cinematic. Electronics age, lubricants degrade, seals stiffen, solder joints go through repeated cycles, sensors drift, thermal stress builds over time, materials behave differently after long exposure. None of that is science fiction. It is ordinary engineering wear happening over extraordinary durations in an environment that gives you no help. That is what makes long missions so dangerous. A planetary mission is not just a test of whether your major systems work at launch. It is a test of whether every small system keeps working after months or years of cumulative punishment. A forgotten valve, a drifting sensor, a degraded seal, a thermal issue in some corner of the system. These are the kinds of things that can become mission-ending when the hardware has to keep going without maintenance support from Earth. And that is why the timeline matters so much. The longer the mission, the more chances the mission gives every weak point to reveal itself. Time becomes a kind of attack. Every extra month is another round of thermal stress, another round of wear, another round of hardware aging, another chance for something small to become something fatal. Then there is another version of the same problem people underestimate badly. What happens when the crew has to leave the vehicle? A lot of people think of the spacecraft as the main system, and the suit as an accessory. That is the wrong way to think about it. On a planetary surface, the suit is a personal spacecraft. If it fails, the mission does not just become harder, it can end immediately. And current suits are not some perfect frontier technology waiting to be used forever, without major redesign. NASA's life support work has been clear that current suits inherited from Shuttle and ISS heritage were not designed for planetary surfaces like the Moon or Mars. That matters because planetary operations are much harsher in the practical sense. More dust, more repeated use, more walking, more bending, more tool handling, more surface work, more wear. And gloves are an especially sharp example. Gloves have limited life, restrict mobility, and contribute to a large share of injuries seen in training and flight. That sounds small until you think through what it means. The crew needs its hands for almost everything that matters during exploration and repair. If the gloves reduce dexterity, work slows down. If repeated use injuries hands, performance drops. If a glove fails, the risk becomes immediate and extreme. So a mission to another planet does not just require a reliable ship, it requires reliable individual life support systems every time a crew member steps outside. And those systems have to work again and again in abrasive environments, under schedule pressure, with high stakes and limited replacement options. That is not a solved frontier toolset. It is still an area where durability, mobility, and maintainability remain serious concerns. And the farther you go, the less acceptable that uncertainty becomes. A short nearby mission can tolerate some limits because help is closer and the duration is shorter. A deep space mission cannot rely on that comfort. It needs systems that can survive repeated use over long periods with much less support. That raises the standard dramatically. Then the last part closes the trap, because the obvious engineering response is also the thing that reactivates all the earlier problems. If hardware fails over time, then the answer seems simple. Add redundancy, carry duplicates, bring spare parts, add backup electronics, add more consumables, add extra tools, add more shielding, add alternate pathways for critical systems. In principle, that is exactly what you should do. Redundancy saves missions. Redundancy is what keeps one failure from becoming total loss. But redundancy has a price, and the price is mass. The moment you say the mission needs more margin, the rocket equation comes back. Every spare component adds weight. Every backup system adds weight. Every extra filter, battery, pump, cable, toolkit, seal, storage unit, protective layer, and reserve tank adds weight. That makes the spacecraft harder to launch, harder to accelerate, harder to land, and more expensive to design around. So the very steps that make the mission safer also make the mission heavier. And that creates one of the cruelest trade-offs in all of spaceflight. If you reduce redundancy to keep mass low, you lose safety margin. If you increase redundancy to improve survival, you make the propulsion and architecture problem worse. There's no clean escape from that. You're not balancing optimism against pessimism. You're balancing launch feasibility against long-duration survival. That is why so many easy visions of planetary travel collapse the moment real engineering starts. Because the real mission is not a sleek science fiction vehicle gliding cleanly to another world. It is a constantly negotiated compromise between weight and resilience, between performance and backup, between what you wish you had on board and what the launch system can actually carry. And by this point, the pattern is hard to miss. Distance makes the mission long. Long missions expose hardware to more wear. Wear demands redundancy. Redundancy adds mass. Mass punishes propulsion. Propulsion limits speed. Lower speed increases mission time. The problems keep feeding each other. That is why reliability over years is harder than launch day. Launch is a violent beginning. Reliability is an endless test with no pause button. And even after all of that, there is still one more ambush waiting. Getting to another planet is only part of the problem. Because after the trip, after the delay, after the radiation, after the hardware survival, you still have to arrive. And arriving safely is its own separate disaster. Getting there is not the end of the problem. In some ways, it is where the most dangerous part begins. People tend to picture landing as the reward after the hard part is over. That is not how it works. For a Mars mission, landing is one of the hardest parts of the entire mission, and NASA treats entry, descent, and landing as one of the highest risk phases of spaceflight for a reason. A mission can survive launch, cruise, navigation, communication delays, and years of system management, then still fail in the final minutes before touchdown. That is what makes landing such a brutal second ambush. All the success before it does not protect you from the fact that the vehicle still has to enter the atmosphere at extreme speed, deal with intense heating, slow down correctly, deploy the right systems at the right times, navigate toward a safe surface location, descend under power, and touch down without destroying the crew or the hardware. And all of that has to happen in sequence, with almost no room for hesitation and no real-time rescue from Earth. That is the part people skip when they talk casually about sending humans to Mars. Deep space travel is not just about surviving the distance. It is also about surviving arrival. A spacecraft that crosses millions of kilometers successfully still has to convert that survival into a safe landing at the very end. If it cannot do that, then the mission has not succeeded in any meaningful human sense. And Mars makes that problem worse in a very specific way. It is not just a planet with an atmosphere. It is a planet with an atmosphere that behaves badly for landing. Mars has an atmosphere only about 1% as dense as Earth's at the surface. At first, that sounds helpful. A thin atmosphere sounds easier than a thick one. But for landing, Mars gives you the worst kind of middle ground. The atmosphere is thick enough to create extreme heating during entry and complicated aerodynamic behavior, but too thin to do enough of the slowing down for you, if your payload is large. That is why Mars is such a hard destination from an engineering standpoint. If you were landing on the Moon, you would deal with vacuum and rely entirely on propulsion. That is hard, but at least it is a clean problem. If you were landing on Earth, you would get far more help from the atmosphere for braking. Mars gives you neither clean simplicity nor strong atmospheric support. It gives you a weak atmosphere that is still strong enough to punish you on the way in. So Mars is too much and not enough at the same time. Too much atmosphere to ignore, not enough atmosphere to save you. That is why landing there is such a nightmare for large payloads. You do not get to choose one clean strategy. You are forced into a complicated sequence of thermal protection, aerodynamic control, parachute deployment, and powered descent, all while dealing with a planet that does not help enough at any stage. And that is exactly where people make another wrong assumption. They look at successful robotic landings and think the problem is basically solved. It is not. This is one of the most important distinctions in the whole topic. NASA's Mars EDL work has made the point clearly that the heritage designs used for robotic Mars landers do not scale to human-class landers. That means the existence of curiosity or perseverance does not prove that landing humans on Mars is just the next step. It proves that we know how to land robotic systems of a certain size and mass under certain conditions. That is a completely different claim. Human systems are bigger. They are heavier. They are less tolerant of failure. They need more life support, more shielding, more structure, more supplies and tighter safety margins. They are not just large robots. They are integrated survival systems carrying people who must remain healthy enough to function after landing. And that means a landing system that works for a rover does not automatically work for a crewed vehicle. This matters because people often hear, "We have landed on Mars before," and assume the challenge has become routine. It has not. It has become demonstrated at one scale. A hard problem solved at one scale can remain unsolved at the next scale, especially when the next scale is much heavier and much less forgiving. Mars landing is exactly that kind of problem. Then the final part makes the whole thing even harsher. A human mission does not just need to touch down, it needs to touch down in the right place. That sounds obvious, but it changes everything. A crewed mission cannot land anywhere safe-looking and call it success. It needs precision touchdown near supplies, habitats, power systems, mobility assets, communication support, and an Earth return vehicle or the infrastructure tied to eventual return. If those elements are spread too far apart, that is not a minor inconvenience. On Mars, it can become fatal. That is why real mission architecture ties entry, descent, and landing directly to planned surface locations and nearby infrastructure. Landing is part of the larger survival system. It has to put the crew exactly where the mission plan needs them to be, not just somewhere on the planet. The romantic version of planetary travel focuses on arrival as a moment. The real version treats arrival as a narrow technical requirement that only matters if it connects correctly to everything that comes next. So the harder question is not, can you land on Mars at all? The harder question is, can you arrive exactly where you must, with the hardware intact, with the crew functional, with the supplies accessible, and with a path toward long-term survival and eventual departure? If the answer is no, then the mission has not really reached Mars in the human sense. It has just impacted Mars in a more controlled way. That is what makes this such a punishing section of the story. First, the distance is hard, then the speed is too low, then rockets punish mass. Then Mars turns into a multi-year exile, then radiation and biology attack the crew, then life support has to behave like a tiny biosphere. Then command and rescue start failing with distance. Then reliability becomes a calendar problem. And after all of that, landing still waits at the end as its own separate crisis. And even if you solve landing, the next truth is even colder. A lot of planets are not just difficult to reach, they are terrible places to be. A lot of people talk about other planets as if the main problem is getting there. But a destination can be reachable in theory and still be a terrible place for human life. That is another major correction in this whole story. Space does not just put worlds far away, it also makes most of them bad targets. Start with Venus, because Venus is one of the clearest warnings in the solar system. It looks like it should be promising. It is close. It is almost Earth-sized. People sometimes call it Earth's sister planet. And then the numbers destroy that comparison. Venus has a surface temperature around 467 degrees Celsius, about 872 degrees Fahrenheit. That is hot enough to melt lead. On top of that, the surface pressure is about 93 times Earth's sea level pressure. That means Venus is not just harsh, it is crushing and superheated at the same time. A nearby world can look familiar in size and still be completely incompatible with human life and with most machinery we would want to send there. That is why Venus matters so much in this argument. It proves that proximity and similarity in appearance do not mean practical habitability. You can be close to a planet and still have no real human future on it. And that should change the tone of the discussion immediately. Reaching other planets does not mean finding more Earths. It means finding out that many worlds fail in much more fundamental ways than people assume. Some are too hot, some are too cold, some have crushing pressure, some have no real surface to stand on. Some are buried inside radiation environments that are bad even for robots. Distance is only one filter. Planetary environment is another, and it removes a lot of the destinations people talk about casually. Then the next correction is even more basic. Not every planet is even the kind of place you can land on. Jupiter and Saturn break that assumption completely. They are gas giants. NASA is very clear that Saturn does not have a true surface, and Jupiter also does not have a solid surface in the normal terrestrial sense. That means when people say going to Jupiter or going to Saturn, they often picture some version of a landing challenge, as if these are just larger planets waiting for better technology. That is the wrong category from the start. You do not solve Jupiter the way you solve Mars. You do not solve Saturn the way you solve the Moon. If you go deeper and deeper into those atmospheres, pressure and temperature keep rising until they destroy spacecraft. There is no stable, familiar ground waiting underneath in the way people instinctively imagine. So these are not difficult colonies. They are not colonies at all. That is an important distinction because it cuts away another popular shortcut in this topic. People often build a mental list of planets as if every entry on the list is basically a harder version of settlement. But many planets are not failed settlement projects. They are worlds that do not offer the physical conditions for settlement in the first place. That means a big part of the solar system is not just difficult. It is outside the category people are pretending it belongs to. Then the next mistake people make is assuming the inner solar system must automatically be easier because it is closer. Mercury destroys that idea. At first glance, Mercury sounds more manageable than outer planets because the travel distances are smaller and the mission times can be shorter. But once again, the environment changes the verdict. Mercury can reach daytime temperatures around 430 degrees Celsius, about 800 degrees Fahrenheit. At night, it can drop to about negative 180 degrees Celsius, around negative 290 degrees Fahrenheit. That swing happens because Mercury has almost no atmosphere to hold heat. So now you get a completely different kind of planetary rejection. Mercury is not rejecting you with distance alone. It is rejecting you with thermal extremes that are hard to handle in both directions. Systems have to survive intense daytime heat and brutal nighttime cold. That means even a relatively nearby world can turn into a serious engineering nightmare once you ask what it takes to keep machinery and people alive there. And that is the larger lesson. Planetary access is not ranked by distance alone. A nearby world can still be almost useless for human presence if the environmental conditions are extreme enough. A farther world can be unreachable for dynamic reasons, radiation reasons, or logistics reasons. Either way, the universe keeps finding different ways to block the mission. Sometimes it uses distance, sometimes it uses atmosphere, sometimes it uses temperature, sometimes it removes the surface entirely. Then that brings the argument back to Mars, and this is where the conclusion becomes uncomfortable. Because Mars is the mild case. That is what should bother you most. Mars has an atmosphere only around 1% of Earth's surface pressure. Its dust creates major operational problems. Its communication delays force autonomy. Its distance forces long mission timelines. Its radiation environment forces shielding and exposure management. Its landing problem is still unsolved at human scale. Its long-duration biology remains uncertain. And NASA has already had to build relay networks, precision landing system, robotic scouts, and years of mission architecture just to operate there reliably with machines. So when people say Mars is the easy planet, that is not really true. Mars is the least impossible serious target. That is a very different statement. It is not welcoming. It is just less openly lethal than Venus, less structurally impossible than Jupiter and Saturn, and less thermally extreme in the obvious sense than Mercury. That does not make it friendly. It makes it the best available bad option, and that distinction matters because it changes how you hear the whole title of this video. If the best realistic target still demands custom communication infrastructure, precision entry and landing, long-duration life support, radiation planning, health countermeasures, autonomous crews, and a huge amount of mission-specific engineering, then what exactly are people assuming about the rest of the planets? That is the tension at the centre of this section. The problem is not just that planets are far. The problem is that most of them are also terrible. Some are terrible because they are superheated and crushing. Some are terrible because they are gas giants with no usable surface. Some are terrible because their temperature swings are extreme. And the best one still looks like a 3-year systems crisis, with weak rescue and uncertain biology. So the dream keeps shrinking under closer inspection. First, you think the problem is building a faster ship. Then you realise the distance is worse than you thought. Then you realise the ship has to survive years. Then you realise the crew has to survive years. Then you realise arrival is its own disaster. And now you realise that even successful arrival may still leave you in a place that does not want you there in any practical sense. That is why other planets sound so much simpler than it really is. The phrase hides the fact that planets are not one category of destination. They are a set of wildly different environments, and most of those environments are either actively hostile or fundamentally unsuited to human presence. The solar system is not a chain of future homes. It is mostly a catalogue of places that reject Earth life for different reasons, and once you accept that, the next layer gets even worse. Because even when the destination is possible in principle, the mission still depends on something quieter that can decide everything: energy, heat, and power. Power sounds like a background issue until you look at what happens when it starts running out. Then it stops being background and starts deciding what the mission can still do. A lot of people think about propulsion, radiation, and life support first, and that makes sense. But none of those systems matter for long if the vehicle cannot keep generating electricity and managing heat. In deep space, power and temperature control quietly move from support roles to survival roles. The first reason is simple and brutal. Sunlight drops fast with distance, not a little. Fast. The rule is basic physics. If you go twice as far from the sun, you do not get half the sunlight. You get 1/4. Go 10 times farther and the drop is much worse. By the time you're far out in the solar system, solar power starts collapsing as a practical resource. New Horizons has already gone beyond 50 astronomical units from the sun. Out there, sunlight is only about 1/2500th of what spacecraft get near Earth. That number should change how you think about the outer solar system. Near Earth, solar panels feel natural, they feel abundant, they feel like the default. But push that same mission architecture outward and the whole balance changes. The farther from the sun you go, the bigger your power problem becomes. Panels that work well near Earth start producing a tiny fraction of that output in the deep outer system. So the issue is not just that the trip gets longer. The issue is that the mission gets weaker while the trip gets longer. That is what makes power such a quiet limit. A destination can be physically reachable on paper, and still become much harder because the energy available to run the spacecraft keeps dropping as you go outward. Power is not just about whether the lights stay on, it controls communication, science, onboard computing, heaters, pumps, valves, fault detection, navigation updates, and everything else that depends on electricity. So when sunlight dies with distance, the whole mission starts losing capability even if the spacecraft itself is still technically alive. Then the next part makes this even more counterintuitive. People usually think space is mainly a place where spacecraft get too hot in sunlight. That is true sometimes, but it is only half the story. The other half is that in deep space, keeping things warm enough becomes its own fight. That is why radioisotope heater units exist. A single RHU gives off only about 1 watt of heat from a tiny plutonium-238 pellet. That sounds almost trivial. 1 watt is nothing in normal life. But in deep space, that tiny amount of steady heat matters because some systems do not fail from overheating. They fail from getting too cold. Electronics, batteries, fluids, mechanisms, and structural materials all have operating ranges. If temperatures drop too far, systems stop behaving the way they should. Materials can become brittle, fluids can stop flowing properly, components can drift out of safe conditions, so a spacecraft going far from the sun has a double problem. It needs energy to run, and it also needs heat just to keep itself alive. That is the part people tend to miss. The vehicle is not only trying to move through space and send data back, it is also trying to prevent its own hardware from freezing into uselessness. Once you get far enough from the sun, your power budget and your thermal budget become tightly connected. If you do not have enough energy, you cannot run everything you want. If you cannot maintain temperature, some of the things you still can run may no longer work correctly anyway. That makes deep space design much harsher than the simplified version people often imagine. You're not just sending a machine into darkness. You're sending a machine that has to stay within narrow thermal limits for years, while the natural energy source most people think of, sunlight, keeps getting weaker and weaker. And that leads to the next problem. Thermal control is not something you solve once and forget. It is a constant balancing act. Every spacecraft has allowable temperature ranges. Components have to stay within survival limits and operating limits during every phase of the mission. That means absorbing heat correctly, storing it where needed, generating it where possible, and getting rid of it when necessary. Even near Earth, this is serious engineering. In deep space, it becomes more punishing because distance keeps changing the environment. Less sunlight means less easy power from solar panels, but it also means colder overall conditions and a greater risk that systems drift below safe temperature ranges. At the same time, internal electronics still produce heat. Some parts may be exposed while others stay shadowed, and different mission phases put different thermal loads on the system. So the farther you go, the more tightly everything starts coupling together. The same distance that stretches your travel time also reduces your solar input. The same lack of sunlight that weakens your power generation also makes thermal survival harder. The same mission duration that increases wear on hardware also increases the length of time that the thermal control system has to keep working without serious failure. This is what makes deep space such a systems trap. The penalties do not stay separated, they reinforce one another. That is why simplistic talk about colonization breaks down so quickly under engineering review. People talk as if distance is one problem, power is another, and heat is another. In reality, they connect. A mission that takes longer needs more durable systems. More durable systems often need more power and tighter temperature control. Greater distance makes that power harder to get. Lower power can force you to shut down instruments, reduce communications, and limit operations. And every time you narrow operations, you also narrow your ability to diagnose problems and adapt. Then you see why weak power changes everything else. Voyager is again a good example. Not because it is failing, but because it shows what survival looks like after decades. A very low data rate matters because it reveals how constrained the system becomes when power and distance both work against you. If your transmitter is weak, your antenna setup matters more. If your power is scarce, you cannot run every instrument all the time. If your thermal margin is narrow, you cannot freely redistribute energy without the consequences somewhere else in the vehicle. That means power is not just one subsystem among many. It quietly governs the rest. It affects communication because transmitters need energy. It affects science because instruments need energy. It affects navigation because sensors, processors, and control systems need energy. It affects diagnostics because the spacecraft has to be able to monitor itself. It affects autonomy because onboard decision-making needs working electronics and reliable computing. And it affects mission lifetime because every power constraint forces decisions about what can stay on and what has to go dark. That is already true for robotic probes, and robotic probes are much more tolerant than human missions. A robot can accept reduced science return. A robot can survive with low data rates. A robot can be designed around narrow operating assumptions. A human mission cannot live inside that kind of austerity nearly as easily. A crewed spacecraft needs strong environmental control, robust computing, medical support, lighting, communications, monitoring, redundancy, and far more active systems running at once. The power demands are not just higher, they are less negotiable, and that is the real pressure building in this section. A robotic mission can sometimes live with scarcity. A human mission often cannot. If robotic spacecraft already face painful trade-offs in communication, science return and thermal survival. After a few decades, then a crewed mission trying to go farther with a much larger support burden is under a much more severe version of the same law. So power and heat decide more than people think. They decide whether the spacecraft can still communicate effectively. They decide whether the instruments still work. They decide whether batteries, fluids, electronics, and structural materials stay inside safe conditions. They decide how much autonomy the mission can support. They decide how much redundancy remains usable. And they decide how long the mission can keep being a mission instead of just becoming an object drifting with fewer and fewer active systems. By this point, the pattern is getting hard to escape. The farther you go, the harder propulsion gets. The harder propulsion gets, the longer the mission takes. The longer the mission takes, the more life support, radiation protection, reliability, and biological endurance matter. Then power and heat come in and quietly limit all of it from underneath. The mission is not just fighting one barrier, it is fighting a stack of barriers that keep tightening together. And once you push past the outer solar system in your mind, the next jump becomes even more severe. Because if power, heat, time, and reliability already make our own planetary neighborhood this difficult, then interstellar space does something even worse. It makes the solar system itself start looking small. The moment you move from planets to stars, the whole conversation changes. Up to this point, the problem has been severe but still recognizably about missions. Once you start talking about interstellar space, it stops feeling like a mission and starts feeling like a sentence. The nearest star system, Proxima Centauri, is about 4.25 light-years away, and one of the most talked about planets there, Proxima b, orbits very close to its own star at about 0.04848 astronomical units, finishing an orbit in just 11.2 days. That contrast matters a lot. Inside a planetary system, distances can be compact enough that planets move around their star on timescales of days, months, or years. But the gap between one star system and the next is what destroys the dream. That is the scale inversion people usually miss. Planetary systems are relatively tight. The spacing between planetary systems is enormous. So when people call Proxima our nearest neighbour, the word neighbour starts to become misleading. It is only a neighbour in the sense that there is nothing closer. It is not a neighbour in any travel sense that means anything human. That is why interstellar travel feels so different from even the hardest solar system missions. With Mars, you are still arguing about engineering, risk, and survival. With Proxima, the distance itself changes the category of the problem. You are no longer asking how hard the trip is. You're asking whether the idea of a trip still means what you think it means when the target is separated from you by years of light travel and by distances that current human hardware barely dents. Then the speed numbers come back, and this is where they stop sounding difficult and start sounding final. Voyager 1 to Proxima would take about 75,000 years. New Horizons launch speed still leaves you looking at roughly 78,000 years. Even if you pretend Parker Solar Probe's peak speed could somehow be turned into a sustained interstellar cruise speed, which it cannot, you still get something like 6,700 years. Those are not missions in the normal human sense, they are breaks in cultural continuity. In that amount of time, languages change beyond recognition. Nations rise and vanish, entire scientific frameworks are replaced. Technologies appear, disappear, and are forgotten. Systems collapse and reform many times. Even recorded history is shorter than some of these travel times by a very large margin. So the problem is no longer whether a spacecraft can keep coasting. The machine can coast. The deeper problem is whether a civilization can remain meaningfully connected to something that lasts longer than everything it usually uses to define itself. If you launch a mission that arrives tens of thousands of years later, who exactly is that mission for? Who owns it? Who remembers why it began? Who still has the authority to speak for the people at the destination? At that point, the distance is not just beating your propulsion, it is breaking the continuity of the culture that launched the vehicle. And there is a very sharp way to make that feel more local. You do not even need to jump to another star to see how slow we really are. Our own solar system already proves it. Voyager 1 would need around 300 years just to enter the Oort cloud, and perhaps 30,000 years to get beyond its outer edge. That means the outer frontier of our own solar system already works on civilizational timescales. A machine launched in the late 20th century cannot even clear our star's distant comet reservoir within anything like a normal human era. That should reset the tone completely. People talk about interstellar travel as if the main obstacle is that stars are far away. But even the outskirts of our own system are already enough to expose how weak our current travel capability really is. That is why the Oort cloud matters so much in this argument. It takes interstellar failure and turns it into a local fact. You do not have to speculate about whether the stars are too far for current propulsion. You can look at what current propulsion means inside our own system and see the answer directly. We do not cross our own outskirts quickly. We are nowhere near treating interstellar distance like a normal extension of solar system travel. We are not even treating the solar system itself as something we traverse on human timescales once you include its true outer extent. And once you accept that, the final implication becomes hard to avoid. At those durations, the mission is no longer a voyage in the usual sense. It becomes inheritance. A multi-generational or millennial mission is not just a transportation problem. It becomes a sociology problem, an ethics problem, a biological problem, and probably a philosophical problem too. Even if you try to keep the language plain, the people who launch the mission would not be the people who arrive. The descendants at the end would inherit a project they did not choose in the ordinary sense. Their entire society would exist inside the mission. Their laws, education, health, conflict resolution and stability would all become part of the spacecraft design, whether engineers want that or not. And that means interstellar travel is not simply a bigger rocket problem. It is a question of whether a human society can stay coherent inside a closed system for spans of time longer than recorded history, while also preserving the technical capability to maintain the mission and the social willingness to continue it. Even if the hardware problem was somehow pushed down, the human problem would still remain immense. Then there is an even sharper question underneath that. If the descendants at the end are born, live, and die entirely within the mission, are they really continuing the same journey? Or are they just the population of a moving world that happens to have an old destination written into its origin story? At that point, the mission is not an expedition. It is a civilization with momentum. That is where the stakes peak in this section. The hard science gives you the setup. The distances are real, the speeds are real, and the timelines are real. The conclusion follows from that. On known propulsion and known biology, interstellar planet reaching is not exploration in the normal expedition sense. It is not a heroic voyage by a crew that leaves home and reaches another world within a meaningful shared human time frame. It becomes either a civilization-long inheritance project or nothing practical at all. So the stars do something the planets do not. The planets still allow you to pretend the problem is only engineering. The stars take that away. They force you to admit that the scale itself may be the barrier. Not because physics forbids motion, but because the distances and timelines push the mission beyond the range where human travel still feels like travel. And once you reach that point, another comforting idea starts breaking too. People often say that even if the stars are far, at least some of those planets might be good targets if they are in the habitable zone. But even that turns out to be much less reassuring than it sounds. A planet being in the habitable zone does not mean it is a good place for humans. That phrase causes a lot of confusion. People hear habitable zone and think Earth-like, comfortable, maybe even welcoming. But that is not what it means. It mostly tells you a temperature-related possibility, not a full environmental verdict. It tells you that liquid water might exist under some conditions. It does not tell you whether the surface is safe, whether the atmosphere is stable, whether the star is calm, or whether the planet is being hit by radiation intense enough to ruin the whole idea. This is especially important around red dwarf stars. These stars are smaller and dimmer than the Sun, so the habitable zone sits much closer in. That sounds helpful at first because the planets are close to the star and can stay warm, but that closeness is exactly where the danger starts. NASA's exoplanet material points out that in those tight habitable zones, X-ray and ultraviolet radiation can reach levels up to hundreds of thousands of times what Earth gets from the Sun. That should completely change how you hear the word habitable. Because now the problem is obvious. A planet can sit in the right thermal zone for liquid water and still be a terrible place for human life. The star can blast it with violent radiation. The atmosphere can get stripped. The surface can get sterilized. The chemistry needed for long-term biological stability can get damaged again and again. So habitability is not hospitality. A planet can meet one narrow condition and still fail almost everything else that matters. Then the next part makes it even harder to ignore, because the most famous nearby candidates are exactly the kind of worlds that sit uncomfortably close to active stars. Proxima b is a good example. It orbits an M-dwarf star at about 0.04848 astronomical units and completes a year in just 11.2 days. TRAPPIST-1e and F are even closer in, around 0.02925 and 0.03849 astronomical units, with orbital periods of about 6.1 and 9.2 days. Those numbers are not just interesting facts to mention in passing. They tell you what kind of environment these planets are living in. They are extremely close to their stars because that is the only way to stay warm enough around a dim red dwarf. And that closeness comes with a price. These worlds are not like Earth sitting at a safer distance from a relatively stable G-type star. They are crowded right up near stars that can be magnetically active, flare-prone, and much rougher on nearby planets. So when people say the nearest exoplanets might be habitable, what they often leave out is that many of them are not calm Earth-like worlds in nice, balanced systems. They are worlds pressed very close to stars that may punish them constantly. That is why the nearest interesting exoplanets are so much less reassuring than they sound. The same geometry that keeps them warm enough may also leave them exposed to flare activity, particle storms, and atmospheric loss. So once again, the problem is not only distance. Even when you finally point to a target and say, maybe that one, the target itself starts looking unstable. Then you get to the most important shift in this section. The stars themselves keep warning us. The more these systems are studied, the less comfortable the easy version of the story becomes. Cool dwarf stars can produce intense flare activity, and that matters because the flare environment is not just a background detail. It can shape the entire fate of the planet. It can damage atmospheres, strip ozone, remove water over time, and change whether the surface remains viable for life as we understand it. And that means the star system can undermine the planet, even if the orbit initially looked promising. This is a very important pattern in the whole exoplanet discussion. First, a planet gets attention because it is nearby and in the habitable zone. Then the details come in. The orbit is extremely tight. The star is active. The radiation environment is harsh. The atmosphere may be under constant attack. And then the whole idea of an Earth-like destination starts dissolving. Not because the planet was fake, but because the label was always much weaker than the people assumed. That is what makes this section hit so hard. The dream keeps shrinking as the data improve. The target looks good from far away because the name sounds good. Habitable zone, Earth-sized, nearby. Then you zoom in and find out the system is much rougher, more violent, and less forgiving than the simplified version suggested. And that leads to the final point. Even if you somehow solve propulsion, mission duration, radiation shielding, life support, reliability, autonomy, and all the rest, the destination list might still collapse under real astronomy. That is the part people do not like hearing. We keep treating exoplanets as backup Earths, as if the main issue is just how to get there. But many of the nearest compelling worlds may be tightly locked to dim stars, heavily flare-exposed, radiation-battered, atmosphere-stripped, or otherwise very unlike the stable conditions humans take for granted here. So even success at the transportation level would not automatically give you a good place to go. That changes the meaning of reachable one more time. A planet can be reachable in principle, and still not be worth reaching for surface human life. A world can qualify as habitable in a narrow geophysical sense and still be a bad destination in any practical human sense. Liquid water somewhere in the model is not the same thing as a biosphere you can trust. The right temperature range is not the same thing as a stable sky, a protective atmosphere, moderate radiation, and long-term biological safety. So the universe does not just make the trip hard, it also keeps reducing the number of destinations that still look appealing after serious scrutiny. That is why this topic gets more severe the more honest you are with it. First, the distances are too large, then the speeds are too low, then the ships become too heavy, then the bodies become too fragile, then the timelines become too long, and even after all that, the worlds at the end may still be the wrong worlds. So by now the argument is not just that reaching other planets is difficult, it is that the difficulty keeps surviving every attempt to simplify it. If you make the travel problem smaller, the biology problem remains. If you make the propulsion problem smaller, the destination problem remains. If you make the destination look promising, the star system may still ruin it. The obstacles do not line up in a single row, they stack on top of each other. And that is why the final section has to land carefully. Because there really are breakthroughs. Real physics is moving, real engineering is moving, but the mistake is thinking one impressive breakthrough turns this whole stack of problems into a solved future. The final mistake is thinking one future breakthrough will suddenly solve all of this. That is how people usually escape the argument. They hear the distances, the radiation, the life support limits, the biology problems, the landing problems, and then they say, fine, future propulsion will fix it, fusion will fix it, antimatter will fix it, some new engine will fix it, but that response only works if propulsion is the one main wall. It is not. Fusion is real progress. It matters. Repeated ignition results are a serious scientific milestone, and an 8.6 megajoule shot is not a small thing. That is real physics moving forward. But there is a huge gap between a milestone in fusion research and a working human deep space transportation system. Those are not the same category of achievement. A lab result is not a space-qualified engine. It is not a complete propulsion architecture. It is not long-duration shipboard power. It is not a radiation-shielded, crew-rated, repairable system that can run for years or centuries without collapsing. That is the pattern people keep missing. A major breakthrough can be real and still be nowhere near the thing they are imagining. Progress in one layer does not erase the many layers still above it. Even if fusion becomes much more practical, you still have to turn it into hardware that can survive launch, survive space, run safely near people, reject waste heat, handle failures, and do all of that in a vehicle that is also carrying habitat volume shielding, supplies, medical capability, redundancy, and a crew that has to stay alive inside it. That is not one missing invention. That is a chain of inventions, plus the engineering discipline to integrate them all into something that does not kill its passengers. And if people think fusion is the serious answer, antimatter sounds even more tempting because the physics looks so extreme. Antimatter is one of those ideas that sounds like the final cheat code. The energy density is extraordinary so. In mass-to-energy terms, it is far beyond chemical propulsion and even far beyond fusion. That part is not fake, the physics is real. But the engineering is brutal, the production is wildly inefficient, the storage is wildly impractical, and that is the point that matters most here. A concept can be physically real and still be useless at mission scale. That is exactly what antimatter represents right now. Not fake science, not nonsense, just something far away from practical use in the only sense that matters for this conversation. Making enough of it, storing enough of it, handling it safely, and building a real transportation system around it, all on a very different level from just saying the energy density looks amazing on paper. So antimatter does not rescue the dream either. It just gives you another example of a true physical principle that is still nowhere near being a realistic answer to sending humans to another planetary system. And that brings the whole argument together. Better propulsion by itself does not solve radiation. It does not solve long-duration life support. It does not solve bone loss, muscle loss, vision changes, or uncertain adaptation to partial gravity. It does not solve communication delay. It does not solve years of maintenance without real resupply. It does not solve landing heavy payloads on Mars. It does not solve getting back off a planet. It does not solve building a stable social system for missions that might outlast nations, languages, and institutions. That is the key point. This is not one wall. It is a stack of walls, and the walls connect to each other. Faster propulsion might reduce radiation exposure, but higher performance systems may bring heat, mass, safety, and reliability problems of their own. Better life support might reduce resupply mass, but it adds hardware complexity and more failure modes. More shielding protects the crew but punishes the launch system. More redundancy improves survival but increases mass again. Every solution enters a network of trade-offs. That is why the title only works if you understand it correctly. Saying we will never reach other planets does not mean nothing will ever move through space. It does not mean robotics stop. It does not mean science stops. It does not mean human spaceflight ends tomorrow. It means something narrower and harsher. Under known physics, observed human biology, and demonstrated engineering, repeatable, crude, civilization-stable access to distant planets is far beyond anything we can honestly call reachable right now. That is a very different statement from saying impossible forever. The point is not fake certainty. The point is scale. People often talk as if the dream is only delayed by a few decades, as if one or two breakthroughs turn this into a normal future. But when you actually stack the real constraints together, that confidence starts looking much less serious. The distances are real, the speeds are real, the mass penalties are real, the radiation is real, the biological damage is real, the life support gaps are real, the command delay is real, the reliability problem is real, the landing problem is real, the destination problem is real. None of that disappears just because one lab result looks promising. So the final truth is not that spaceflight is fake. It is not that exploration ends. It is not that human beings will never leave Earth again. The harder truth is that the fiction version of this future trained people to expect the wrong kind of progress. It taught people to expect that once the engines got better, the planets would become normal destinations, but the universe is not arranged that way. It did not just put planets far away. It made distance interact with speed. It made speed interact with fuel. It made fuel interact with mass. It made mass interact with launch and landing. It made long missions interact with radiation, hardware decay, psychology and biology. It made weak sunlight interact with power and heat. It made communication delay interact with autonomy and stress. It made the nearest promising worlds uncertain, and the nearest stars so far away that the mission starts breaking culture itself. That is why this argument survives every attempt to simplify it. You're not stuck waiting for one invention, you're facing an entire architecture of constraints. And as far as we can honestly see right now, that architecture is much stronger than the stories people like to tell about human expansion into the cosmos. So the real meaning of we'll never reach other planets is not that no machine will ever go farther. It is that the dream of humans casually reaching other planets the way fiction taught you to expect does not look like a delayed version of the present. It looks like something that would require a different level of physics, engineering, and civilizational endurance than we currently possess. And maybe we will build some of that. Maybe we will not. But if we do not say how far away that level really is, then we are not being honest about the universe we actually live in. And that is the ending. Not that the dream's childish, not that the effort is pointless, but that reality is much harsher than the dream. The planets are not just far away. They are protected by distance, time, hostile environments, fragile biology, and unforgiving engineering all at once. And until that changes in a way we can actually demonstrate, the idea of humans reaching other planets in a normal, repeatable, civilization-stable way is not the next chapter. It is still beyond the edge of what we can truthfully call a human future. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.